Hello everyone, in this video I'll be talking about UV visible spectroscopy and the topic is chromophore. By the way, my name is Fayaz and I'm doing a PhD in chemistry, in organic chemistry at UNSW Sydney, Australia. And this is my YouTube channel, and for your information, I have uploaded more than 106 videos on my YouTube channel related to various aspects of organic chemistry and scholarships for foreign PhD admissions. So in my YouTube channel you can find videos about retrosynthesis, NEM reactions and natural product chemistry, tutorials about how to write an email to a foreign supervisor for getting PhD scholarships, and you can find videos about how to apply for PhD admissions and scholarships abroad, or how to write a review article and how to write a research paper, and several spectroscopy videos about IR spectroscopy and NMR spectroscopy, and most of the videos about organic chemistry, their NEM reactions and their synthesis mechanisms, simple general concepts of organic chemistry, nomenclature and simple things. So I'll be adding more and more videos on my channel, so please keep watching this channel and share the link with your friends, and don't forget to subscribe it. Let's come back to our topic. So in this video I'll be talking about a chromophore, and by the way, let me tell you one thing, that I'm following a book for this video, and the name of the book is Introduction to Spectroscopy by Pavia. So in this video I have taken notes from that book, and the topic that we will be covering today is chromophore. So first we will discuss what is chromophore and how we will learn about the chromophore. Okay, so although the absorption of ultraviolet radiation results from the excitation of electrons from ground to excited state, so there is a ground state, there is an excited state, so there are incoming radiations or energy, and there is an electron which absorbs energy and goes into the excited state. Excited state is higher in energy and ground state is lower in energy. So that what the first line means, that although the absorption of ultraviolet radiation results from the excitation of electrons from ground to excited states, the nuclei that the electron holds together in bonds play an important role in determining which wavelengths of radiation are absorbed. The nuclei determine the strength with which the electrons are bound and thus influence the energy spacing between ground and excited states. Hence, the characteristic energy of a transition and the wavelength of radiation absorbed are properties of a group of atoms rather than of electrons themselves. The group of atoms producing such an absorption is called a chromophore. That is how we define a chromophore: any substance that has the ability to absorb radiations. Structural changes occur in a chromophore, and the exact energy and intensity of the absorption are expected to change accordingly. So different structure have a different chromophore, are different properties, are different bonds, different functionalities, different groups. So the absorption properties will change according to the structure. Very often it is extremely difficult to predict from theory how the absorption will change, as the structure of chromophore is modified, and it is necessary to apply empirical working guides to predict such relationships. That is the chromophore. So first we will discuss alkanes as a chromophore, then alkenes, alkynes and all of the organic functional groups as chromophores. So alkanes, as you know, they are the saturated hydrocarbons. They do not contain any functionality. There is a sigma bond present in between them. There is no free unpaired electrons present in alkanes, and they do not contain any degree of unsaturation, neither they contain a double bond or something like that. So for molecules such as alkanes that contain nothing but single bonds and lack atoms with unshared electron pairs, the only electronic transition possible are for the sigma to sigma star type. So you can easily tell that what kind of electronic transition is present in alkanes, that is sigma to sigma star. whether it's a linear alkane like this or whether it's a cyclic alkane like this, they all have one electronic possible transition, that is sigma to sigma star. Why? Because they do not contain any double or triple bond and they do not contain any unshared electron pairs. These transitions are of such a high energy that they absorb ultraviolet energy at very short wavelengths, shorter than the wavelengths that are experimentally accessible using typical spectrophotometers. Figure 7.6 illustrates this type of transition. The excitation of the sigma bonding electrons to sigma star antibonding orbital is depicted at right. So let's discuss now alcohols, ethers, amines, and sulfur compounds. In saturated molecules that contain atoms bearing non-bonded pair of electrons, transitions of N to sigma star become important. So alcohols, they contain oxygen, so this is H and this is R. So these are called alcohols and they contain these free unshared pair of electrons. That's why they are going to show N to sigma star. And these are the ethers, that is R, oxygen, and R. And they also contain free unpaired electrons, hence they also show N to sigma star. Amines, that is R, NH2, and they also contain this free unpaired electrons, that's why they show N to sigma star. And any sulfur containing compounds like thiols or SH, so they also behave same like alcohols, they contain free unpaired electrons and hence they show N to sigma star electronic transition. But let's have a look at the sigma to sigma star transition. So we have a carbon single bond, and then when this is excited, when it absorbs energy, then it goes to excited state. So these are the two sigma electrons. When they absorb energy, they go to sigma star, that is higher in energy. So this is how this transition takes place, sigma to sigma star transition. But alcohols, ethers, amines, and sulfur containing compounds, they show N to sigma star transition. Why? Because they contain non-bonding pair of electrons. This is how this N to sigma star transition takes place. We have amines, they contain lone pairs, and you can see this is the N electrons, they go into the sigma star. So this is N to sigma star. These are the free lone pairs on nitrogen, they go into the sigma orbital, hence giving rise to N to sigma star type of electronic transition. So this is a continuum. They are also rather high energy transition, but they do absorb radiation that lies within an experimentally accessible range. Alcohols and amines absorbs in the range 175 to 200 nanometer, while organic thiols and sulfides absorb between 200 to 220 nanometer. Most of the absorptions are below the cutoff points for the common solvents, so they are not observed in solution spectra. Figure 7.7 illustrates the N to sigma star transition for an amine. The excitation of the non-bonding electrons to the anti-bonding orbital is shown at the right, this one. Alkenes and alkynes, they contain double and triple bond. With unsaturated molecules, we are going to have pi to pi star transitions become possible. These transitions are of rather high energy as well, but their positions are sensitive to the presence of substitution, as will be clear later. Alkenes absorb around 175 nanometer and alkynes absorb around 170 nanometer. Figure 7.8 shows this type of transition. Carbonyl compounds, unsaturated molecules that contain atoms such as oxygen or nitrogen, may also undergo N to pi star transition as well as pi to pi star transition. These are perhaps the most interesting and most studied transitions, particularly among carbonyl compounds. These transitions are also rather sensitive to substitution on the chromophoric structure. The typical carbonyl compound undergoes an N to pi star transition around 280 to 290 nanometer with a molar absorptivity of 15. Most N to pi star transitions are forbidden and hence are of low intensity. Carbonyl compounds also have a pi to pi star transition at about 188 nanometer with an molar absorptivity of 900. Figure 7.9 shows the N to pi star and pi to pi star transition for the carbonyl group. So this is the pi to pi star transition for alkenes, and you can see here. So these are the pi electrons. They go into the excited state and into the pi orbital. These are the electronic transitions of the carbonyl group. They show two types of transitions. One is N to pi star and another one is pi to pi star. So we have N orbital, we have sigma orbital, we have pi orbital, we have N, we have pi star, and we have sigma star. So this is the carbonyl group, which contains free unpaired electrons at the oxygen atom, and this is how they go into pi to pi star. So there's a double bond between carbon and oxygen. The lone pair of the pi electronic cloud shared between carbon and oxygen goes into the pi star orbital, giving rise to a pi to pi star transition. Whereas N to pi star transition happens because these electrons are present at the end. These are unshared pair of electrons, these ones. So they go into the pi orbital. So this is N to pi star transition. And this is the pi to pi star transition of the carbonyl groups. Table 7.3 lists typical absorptions of simple isolated chromophores. You may notice that these simple chromophores, this is the table 7.3. You may notice that these simple chromophores nearly all absorb at approximately the same wavelength from 160 to 210 nanometer. The attachment of substituent groups in place of hydrogen on a basic chromophore structure changes the position and intensity of an absorption band of the chromophore. The substituent groups may not give rise to the absorption of the ultraviolet radiation themselves, but their presence modifies the absorption of the principal chromophore. Substituents that increase the intensity of the absorption and possibly the wavelength are called auxochromes. Typical auxochromes include methyl, hydroxyl, alkoxy, halogen, and amino groups. Other substituents may have any of four kinds of effects on the absorption. Either they show bathochromic shift or red shift, or they show hypsochromic shift, blue shift, or they show hyperchromic effect, increase in intensity, or they show hypochromic effect, a decrease in intensity. So bathochromic shift means a shift to a lower energy or a longer wavelength. Hypsochromic shift means blue shift to a higher energy or shorter wavelength. Hyperchromic effect means an increase in intensity, and hypochromic effect means decrease in intensity. So these are the typical absorptions of simple isolated chromophores. If we have simple alcohol, then we would see a transition for alcohols is n to sigma star, and lambda max will be 180 nanometer, and the molar absorptivity will be 2.5. If we have ethers, they also contain oxygen, and oxygen contains unshared pair of electrons, and we will observe a n to sigma star transition, and the lambda max will be 180 nanometer, and the molar absorptivity would be 3.5. If we have amines, they also contain free unshared pair of electrons at the nitrogen, and this will give you n to sigma star transition. And the lambda max is 190 nanometer. We have thiols, they appear at n to sigma star, and the lambda max is 210 nanometer. When we have alkenes, they contain pi electrons shared between two carbons. Then we will observe a pi to pi star transition for alkenes, and the lambda max will be 175 nanometer. But if we change the R groups, then the lambda max does changes with the R groups. But this is a base value. For alkynes, simple alkynes, then we will see there's a pi electrons between carbon and carbon. We will see a pi to pi star transition, and the lambda max will be 170, and the molar absorptivity will be 3.0. For nitriles, they also contain pi electrons shared between carbon and nitrogen, and the nitrogen also contains the free unpaired electrons which are not bonded to anything else, hence they give rise to n to pi star transition. The lambda max is 160, and the molar absorptivity is less than 1.0. Azo group, which is very common, and these are the photoswitchable molecules. They respond to light of certain wavelength, and they adopt cis or cross conformation upon certain wavelength of radiation when they are exposed to it. And they also have n to pi star as well as pi to pi star transition, because n to pi star transition because there is a pi bond between nitrogen and nitrogen, and there is a free unshared pair of electron between nitrogen, and that is due to the n to pi star transition. That is with the azo group. And the lambda max for this group appears at 340 nanometer, and the molar absorptivity for this one is 1.0. Next class of functional group is nitro groups. They also contain free lone pair of electrons at oxygen, and there's a pi bond between oxygen and nitrogen. So the electronic transition that will be responsible for this chromophore, that is called n to pi star transition. The lambda max for this group appears at 271 nanometer. Next functional group is aldehyde, and that is a chromophore which contains double bond between carbon and oxygen, and it can give two types of transition. One is pi to pi star transition, which appears at 190 nanometer, lower in wavelength, higher in energy. And second transition that can happen for aldehyde is n to pi star, and the lambda max for this transition is 219 nanometer, and this transition is lower in energy but higher in wavelength. Next functional group is ketone. This, like aldehyde, can give you two types of electronic transitions. One is called pi to pi star, and another is called n to pi star. And pi to pi star appears at 180 nanometer, and n to pi star appears at 280 nanometer. Next functional group is carboxylic acid, which contains free lone pair of electrons with oxygen, and it can also show n to pi star transition, and the lambda max for this functional group is 205 nanometer. And next functionality is ester, which also contains free unpaired electrons attached with oxygen, and it can show N to pi star transition, and lambda max for this functional group is same like carboxylic acids at 205. Next functional group is amides, where we observe N to pi star transition and the lambda max is 210. These are the important electronic transitions for major functional groups, and these we call in UV visible spectroscopy as chromophores, and these are the simplest electronic transitions when there are no electronic substituents attached. So we are just saying this is the R group, and this R group influences the lambda max. If there's electron donating groups, they sometimes increase the wavelength, and when there's electron withdrawing group as R, then they sometimes decrease the wavelength of a chromophore. So if you have any question regarding this topic of chromophores, feel free to drop down your comments below in this video. I'll be happy to get back to you. Thanks for listening. Take care. Bye.